This conference will now be recorded.
Hi everyone, thank you for joining. I'm Malakum Merit, electrical engineer at Facebook. This presentation is about specification we created to address data center electrical system stability. I'll talk about why we created this spec, what the spec covers, along with analytical work, field measurement data, and some recommendation how to improve the electrical system stability. The main reason we created this spec is we needed to ensure our data center are electrically stable by design, so we don't have to go through same resonance issue we have in the past. We also wanted to have a spec which covers end-to-end system, not just a component level. And in addition, we want to minimize system voltage imbalance as low as possible. A quick history: a couple of years ago, Facebook experienced a system instability and resonance at multiple data centers located at different regions. The entire system was oscillating, which led to high harmonic current. The operators heard a huge noise, sounds like a washing machine. So what you see here is the current waveforms from the main switchboard's MSB. So as you can see, the current was bouncing up and down, oscillating, and instead of being a flat, clean sinusoidal wave. So this was very bad downstream for the power supplies. If we look at the trend over time, we saw that there was a huge spike in power, active power in the green as the load increased. And similarly, we saw a huge neutral current, as you can see here, as the load increased. So we did a thorough investigation and we identified that it's the impedance interaction between the building electrical system and the power supplies are the root cause for this resonance. So let's look at the electrical system. Our electrical system composed of Facebook substation fed from utilities. We have the medium voltage switchgear feeding our medium voltage to low voltage transformer. And we have the main switchboard MSB, which is also fed from the backup generator. The power goes to our low voltage switchboard SP, our line reactor, reactive power panel RPP, and to the distribution busway, which feeds multiple rows of racks. And all these paths, we call it a normal power path. We have a multiple redundancy paths. One is the main switchboard bypass circuit to bypass the main switchboard, and an additional bypass at the SB RPP level. So we define our building electrical system as everything from the utility all the way to the power supplies, the PSUs. So they are the source impedance of the power supply. So we define as CFS, and the power supply being the load. So we transform that to an equivalent single phase zero sequence, negative sequence, and positive sequence circuit with an ideal source, an input, and an output impedance for analysis. So each component contributes to an impedance, and it's represented by a 3x3 matrix. The diagonal elements are the self-inductance of phase A, phase B, phase C, and the off-diagonal are the mutual inductances between phases, say between phase A and B, phase A and A, C. So we analyze this complex non-homogeneous power paths from the utility to thousands of power supply, including some of them fed from the reserve paths, some are fed from the normal paths. So we have multiple paths, multiple thousands of power supplies. So we have to reduce this to a manageable scale for analysis. So we reduce that to a single equivalent impedance using impedance scaling and eigenvalue analysis. So now the system can be determined by testing the power supply, just a single power supply, with a source impedance, which is equivalent to the building impedance seen by one single power supply. It's defined by this equation here. And then we define a matrix called base impedance ratio, BIR, which indicates whether the system is stable or not, or how good the system is in terms of stability. So this BIR is defined as the ratio of the base impedance of the power supply divided by the building power supply. And basically, the higher the BIR, the better the system stability. The system is more stable if the building has very low inductance, and then, or if the power supply has high input impedance. So we created the building requirement based on our field measurement data from multiple sites and the testings with the power supplies in the lab. So we have this requirement for our buildings, and we came up with this magic numbers 2.5, and if the building's total building impedance BIR is above 2.5, it's a pass. If our BIR is below 1.5, it's a fail. And anything in between is a marginal pass or marginal fail. And similarly, we created a requirement for each power supply vendors and give it to them. The requirement for this power supply is they have to, if they can work with a very, very low BIR, it's good, it's a pass. If they cannot work with a good building with higher BIR, that's a fail. And in between is marginal fail and marginal pass, obviously. And we did this impedance measurements at different sites for North America, one in in Ireland, one in Leeds centers, to get an idea of how our system look like and how to get those numbers. This is the impedance measurement techniques we use. As you can see here is an impedance analyzer called CPC 100. And these are the device under test. It has 4 inputs, phase A, B, C neutral, and 4 outputs. So we short all the output phases together, A, B, C, and neutral, with a jumper cable, as you can see in this picture. And we inject current, a high current, between phase and neutral. And we measure voltages between phase A, B, C, and neutral. And based on those voltage and current measurement, we can calculate the inductance. So, for example, if we inject on phase A, measure the voltage on A and neutral, we get this self-inductance on phase A. If we inject on phase A, measure the voltage on B, C, that gives us the mutual impedance between phase A and phase B, and so on. We also take this field measurement and plug into our software model to see whether the system is stable or not. So this is an example of a system which is stable. As you can see, we increase the load from 0 to 100% through time, and the voltages were lower but stay stable. And if you look at the rack currents, they also go up from 0 to full power over time, but they're still stable. If I show you an example of a failed BSUs, power supplies, you can see when we increase the load, certain point, around 60% load, they start to oscillate. These are the unstable rack voltage. Similarly, you can look into the currents, unstable currents here as around 60%. So this model is help us validate our system with the power supply model before we even put the servers into our data centers. So we have a specification for the building, and then we extract for those buildings to create an impedance space for every single component. So again, the core goal of this impedance spec is to ensure system stability by design. And we specify the inductance limit for every single component, including switchboards, reactors, busway, even cables. And we have 3 parameters: the average self-inductance, which is the average of A, B, and C inductances. We also specify the self-inductance deviation, which indicates how bad the voltage imbalance is. The higher the deviation, the higher the voltage imbalance will be. And we also have the average mutual inductance. So here, an example for the main switchboard, we have 12 microhenry for the average impedance, and then we have 65 micro for the reactor and 13 for the busways. These numbers came from multiple data we collect from different sites, and also we test them with a power supply, different firmwares in the lab before we come up with these specific numbers. We are engaging vendors to meet this spec, and not only to meet this, but also to develop the process of testing this impedance, give us a proof of compliance. And we are currently working on all the vendors. This tells us how the impedance contribution of each component in our data center. As you can see here, we have a huge contribution by the reactor and by the main switchboards. And that tells us where we need to focus on reducing the impedance to be more stable. And we engage vendors based on that, and we prioritize engaging reactor vendors and switchboard vendors. We test multiple vendors' switchboard products, about 5 of them. And if we look at each vendor's impedance values with the spec, we have only one vendor that's in the fail region, because our spec is 12 micro. Even with this vendor, we worked, and the latest version actually passed the spec. If we compare the mutual inductance, we have 2 vendors which fail the spec, but currently most of them pass, including some of these vendors' latest design. This is the inductance deviation. which is good that every vendors pass the spec. So based on measurements, modeling, lab testings, we have a lesson learned and we have recommendation on how to improve the system stability. One way to improve the system stability is to find the weakest link. And we notice zero sequence is the weakest link, which has the highest inductance. Sequence in the matrix, the zero sequence has the phase plus 3 times the neutral. So in our system, all the high voltage, the medium voltage, and delta, which means there is no zero sequence current flowing past the PTX, which delta to star connection here. So in general, if we make all the system delta configuration, our zero sequence would be minimal. So delta configuration is better for sequence stability, for zero sequence stability in particular. So recommendation number 1, try to make delta configuration as much as possible or move the neutral as low as possible. Second thing we notice is the phase arrangements between neutral and phases. So currently we have a cable bus that has this arrangements between phase conductors. That's 6 conductors per phase. All the neutrals are on one side, then we have phase B in the middle. We consider this as a poor phase arrangement. So if we propose a different arrangement, all the phases, mix it up, move the neutral in the middle, we saw a huge decrease in impedance, almost by half. So the phase arrangement is a key to reduce cable impedance. And the other thing we observe is the difference between the single-phase core reactors and 3-phase core reactors. So our current reactors is made from 3 single-phase core, so there is no mutual coupling between each phase core, so the mutual coupling is almost 0. But if we look at our RPPs, which is made from 3-phase core, the mutual inductances are negative. So a negative mutual inductance is good because it will actually reduce the overall impedance. So if we change from single 3-core phase reactor to one 3-phase core, the BIR can be improved from 2.8, say 2.5. That's a huge improvement. So what we're saying is 3-phase core reactor are really good for system stability compared to having independent 3 single-phase cores. I would like to thank Dr. Jensen, who is a professor at RPI and also an independent contractor at Facebook. I would like to thank multiple guys in Facebook and from DCD, SND, FACING, and Hardware for their contribution. And with that, I will open to questions.